Now we turn our attention to waveguides. So far, we have considered thin films deposited on substrates, and light has passed through the thin films. The waveguides are often also dielectric layers on substrates, but light is confined in the thin film. Basically, the confinement of light is due to reflection at the interfaces. Reflection is provided by mirrors or total internal reflection, and there are several characteristics that are used to describe such a light confined in a waveguide. We take a look at these different phenomena and definitions. The light field bouncing back and forth between the reflective surfaces creates a mode which has a so-called effective index. The effective index describes the propagation of a mode in a similar way as the refractive index describes propagation of a plane wave. So it has a similar phasor form where the complex phasor presents the wave propagating in the positive z direction. The mode field describes how the energy is distributed in the waveguide. For example, we are interested how big part of the power is inside the waveguide and how much is located outside the waveguide. Polarization of the mode describes the orientation of the electric and magnetic fields. Our mode is all the time propagating in the positive z direction. If the electric and magnetic field are both perpendicular to the propagation direction, our mode is so-called TEM, which is transverse electric magnetic polarization. If our electric field is transverse to the propagation direction, we have a TE polarized mode, transverse electric. Similarly, magnetic field can be transverse to the propagation direction. In this case, we have transverse magnetic or TM polarization. Finally, our mode can have all the components both in the transverse direction and propagation direction, and in this case we have a so-called hybrid polarization mode. The definition of the TE and TM polarization follows closely the one we have already studied in plane waves. Then we are interested in number of propagating modes. Depending on wavelength and dimensions of the waveguide, we can have several profiles of the mode fields, and the number of possible modes determines if we have a single mode waveguide or a multi-mode waveguide. In a single mode waveguide, only the so-called fundamental mode is propagating. Finally, the numerical aperture is a measure of the angle that allows coupling of light into the waveguide. In case of high angles, light does not stay in the waveguide, but with an angles within the numerical aperture, light stays in the waveguide. There are several waveguide configurations. The first one is the mirror waveguide that basically consists of two plane mirrors, and the light is bouncing back and forth between the mirrors. In the second case, we have dielectric materials, and the mirror is formed by total internal reflection at the material's boundaries. And this is often called a slab waveguide. In the next waveguide, we have a slab in vertical direction and a rib in the horizontal direction. So the light is confined in two different directions, while the propagation takes place along the rib. When the dimensions of the rib are reduced, we have a wire waveguide with very small dimensions, and the mode is confined also in vertical and horizontal directions. In the next waveguide, we have a slab and a rib made of different material. Finally, we have a waveguide which is completely buried in dielectric material. The mode is confined in vertical and horizontal directions.